Hello, welcome to a new series on electrodynamics, and my name is Anurag Nigam, and the objective of this playlist is going to be explore various tools which are available in the market which you can use for electromagnetic simulation. And I have named it electrodynamics. There is a very minute or subtle difference between electromagnetics and electrodynamics. Electrodynamics has to do more with the moving objects, more to do with the time varying field. Electromagnetics has to do with the electric and magnetic forces, right, which act upon a body, right, a charged body maybe. So I'm not going to explain in detail what is the difference between electromagnetics or dynamics, but let's get started. So now we have a number of tools which are available for electromagnetic simulation, and whenever we talk of electromagnetics, people think of antennas, filters, but that's a very small portion of electromagnetics. Electromagnetics is going to be doing with passives as well as the routing and the passive components on chip. So it is also involved in MMIC designs and all that, or MIC designs. Okay, so the whole range goes from boards to ICs, right, when it comes to EM simulation, right? And then the whole range goes from the lumped elements like capacitors, inductors, and in some cases resistors also at high frequency, right? And then there are distributed elements like transmission line based components like hybrids, dividers, combiners. Then you have got 180-degree hybrid, you have got directional couplers, you have got launch coupler, for example, you have got other things like what I will say, even magnetics is involved, for example, in circulators and things like that. So all this can be simulated, right, using these EM simulators. So let's have a look at what's available in the market, and where it makes sense to focus, and which one you would be more comfortable with. Now it's a personal choice, right, which tool you are comfortable with, but more or less inside they are almost the same. So I'm going to start with first thing is this Keysight Momentum. Now this Momentum is a method of moment based 2D solver which has been expanded through some algorithms to involve some currents in z direction also. So that's why it is called 2.5D solver. So this method of moment is a frequency domain technique where we are trying to find out the exact solution of the currents, right, when a certain excitation, that is the voltage, which is applied, right? So in that case you take a geometry which is usually planar. So what I mean by planar is that it is made up of sheets of metal, right, which are separated by dielectrics or which may be connected by vias. So that is called planar. So it's in one plane, xy plane, and the z direction is basically a algorithm. It's a computation of z currents. So in method of moment there is nothing to consider z currents, right? So thick metals cannot be considered in method of moment per se, but when you say 2.5D simulator, you can use some algorithm to work on the z direction currents, right? So this method of moment is a part of, or this momentum, it is called momentum in ADS. ADS is a tool from Keysight which is used for circuit design, for lots of things in to do with the EM and all that stuff. So that is Keysight Momentum. It's a method of moment based tool. Now there is another extension to that tool. In Momentum they have also allowed you to do finite element or finite volume method, right? So that also can be done in Momentum, but my experience shows that the Momentum is more accurate compared to the FEM implementation in Keysight ADS, right? So you have to be careful. So when you are using Keysight ADS, you should be using Momentum, not the FEM. FEM is just an add-on. If you really want to do finite element method, right, then there is another tool from Keysight which is called EMPro, right? So EMPro basically allows you to design 3D, full 3D, right? So here what you can do is you can do a finite volume method. And now I did some designs and I compared momentum results with FEM results in ADS and FEM results from EMPro. So FEM results from EMPro match the momentum results of ADS, but then the momentum results of ADS do not match very well with the FEM results from ADS. So FEM, keep in mind, is an add-on, and I won't recommend using FEM in ADS, right? If you want to use FEM, you use EMPro, and EMPro and momentum results are same, while the FEM results from momentum are different from the MoM results from momentum. So you have to be very careful in high frequency designs, unless sometime in the future this company figures out why the results are different, right? So that's just a word of caution. Okay, so now between the two tools, okay, you can do a single button export to EMPro. So if you have done a planar circuits, which is easy to lay out, right? It is layout in 2D, and then the profile is defined by the substrate. So once you have done a layout, you can export that with one click of a button to EMPro, right? And then you can do a FEM simulation in EMPro, and then take the design or the results back to ADS. So we are going to see how to use ADS, how to set up a simulation in ADS with one example, and then we will see how to export this to EMPro from ADS, right? So you can do a validation between the two tools. Okay, now moving forward, we also have got this Xfdtd. Okay, so this Xfdtd is a finite difference time domain method, but they say Xfdtd because they could not patent finite difference time domain method, because it's patented with Alan Teflov and Susan Hagnes, right? Or it is with Yi. So Fdtd could not be, it could not be called Fdtd. It is finite integral time domain method. So that's what they call it. Though in basics, both are the same, right? The way they solve the equation in time domain by decoupling them on two grids, one for the H, one for the E, which are basically staggered. So that's how you decouple the curl H and curl E equations, okay, by having two separate meshes, which are staggered in the space. Also, we are doing computation on half time steps. Okay, so that means that's also staggered, right, for E and H. So by linear interpolation, you will be able to do the what you call at any point you can compute the E and H fields. So that's what Xfdtd is going to do. It's from now it is the intellectual properties with REMCOM, right? But then this is the same algorithm which is by Alan Teflov and Susan Hagnes. Now this Xfdtd, some rights were bought out by Keysight, earlier called Agilent, and that is incorporated as Fdtd simulation in your EMPro. So EMPro allows you to do finite volume method where the meshing, okay, so what you do is you draw the geometry and you put the excitation, which is the ports, right, and then you mesh the geometry, right, and so that meshing is in form of tetrahedral cells, and the E and H are defined at the vertices and the mid of the edges, and everywhere else it is going to be a approximation. So this is a finite volume method which is used in EMPro, and the meshing is adaptive. So basically, once you do a simulation, you find out an error function, and then you remesh it, right, with a finer grid, and try to see what is the difference between the two computations. And then if there is a lot of difference, then you are going to do an even finer mesh till this difference of results, okay, becomes small. So when this becomes small, it goes ahead and does the finite volume method, right? So that's how adaptive measuring is done in EMPro. And by default, the edge on these meshes should be at least 1/10 of the wavelength. So meshing, basically you have some control to intervene. You can decide the meshing in different parts of the geometry, but then it is highly automated and you can rely on the results of an automated mesh, right? You do not have to insert your own settings for the meshing. Okay, so that's what is finite volume method doing. Now finite difference time domain method, you are going to divide this in cubic cells. So everywhere the cells are going to be cubic. Now the smaller the feature size, the smaller is going to be the cubes, right? So now if you discretize a large object with the cells which represent the smallest feature, then it is going to become very elaborate because the number of cells are going to be large. Now in that case, it is a possibility to do adaptive meshing. So in finer features you can do smaller cuboids, while in bigger features you can do bigger cuboids, and then you will be able to do interface. Now what's the advantage of Fdtd over FEM? FEM basically is a frequency domain technique. It is based on inversion of a matrix, right? Now there are two methods in there. One is called the direct, other is called the iterative. Okay, so in direct, what it's going to do is it is going to compute fields everywhere. Okay, it's a direct computation, right? While in case of iterative, okay, once you need a field at a point, okay, the adjoining points you can basically iterate out. Okay, so that's going to be faster because you are not looking for convergence at all the points, but you are looking at convergence at few points, and then you are going to do an incremental stepping from that initial guess on the nearby points in the region, and you'll be able to do it faster. So there are two ways of running this FEM. One is called the direct method, the other one, and it is going to be slow, and the matrix would be n, let's say n by n, then the number of computation is n cube for inverting a matrix, right? So that would be the direct method. In iterative method, okay, you simplify this, so it runs faster but it is less accurate. So iterative methods can be less accurate compared to direct method in finite volume method or FEM, right? So that's what's happening in FEM. Now in Fdtd, right, the cell is a cube, right? So once the cell is a cube and everything is defined on the edges of the cube, as soon as you take a diagonal distance between the two vertices in a cube, there is going to be a dispersion, and that dispersion has to be within a certain, that dispersion is an error, and it has to be bound with a certain maximum dispersion which you are going to see along the diagonal. Okay, so that is called current factor S, should be less than 1, right? So dispersion in Fdtd grids is more important. Now how do these two, FEM and FEM, deal with fields which are far away? So what they do is you box the object, the object which is under consideration, where you calculate the currents and then the related fields, currents and voltages and related fields E and H, right? You do it in a smaller geometry, but then you put it in a box, and once you collect all the field at the edges of the box, you can apply certain transformations to transform the near field to far field. So that's how the antennas are simulated. Antennas are simulated in a small box, and once you do the simulation, all the surfaces of the boundaries of the box is where the near fields are totally absorbed, or numerically they are not reflecting back in, right? Once you do that, you will be able to transform that near field information into what you call the far field through certain transformation. So that's how the antenna patterns are computed. It's not that the entire space is discretized up to a far field region. No, they are computed in the near field and then a transformation is applied. That's how antenna patterns are computed. Now in Fdtd, the same box concept is there. Okay, you put an object inside a box, but then this box has certain properties, like it can be a perfectly matched layer, or PML, which basically absorbs all the radiation thrown at it, but not in all the incidence angles. Okay, so perfectly matched layers are basically, numerical adjustment to collect all the fields without reflecting them back in. So it depends, the reflection depends on the incidence angles. So when you look at corners of this box with the geometry inside, the corners are going to light up because there the incidence angles are different, right? So there's perfectly matched layers. Okay, there are different implementations of PML. Okay, some of them are very good in some frequencies, some of them are not so good. So PML is that you have a box, the geometry is inside, the box boundaries are all perfectly matched layers. Okay, so and whatever is gathered by this PML, that is going to be transformed into your far field. Now in Fdtd, another thing which they do is what is called absolute absorbing boundary conditions, right? So you do a absolute absorption. So this is more like a anechoic chamber, like when you test an antenna in an anechoic chamber, whatever is thrown at the walls of the chamber, they all absorbed by the cone structure, which is coated with some kind of a dielectric material to absorb everything which is thrown at it. Okay, so that there is no ripples reflecting back into the space. So same anechoic chamber concept is there in Fdtd, which is absorbing boundary conditions. Okay, and these absolute absorbing boundary conditions are made up of cells of certain thicknesses. Like for example, the boundary may be made up of cells which are like 3 cell thick boundary or 5 cell thick boundary. So that adds additional space in computation, and these cells are basically the material defined there is going to be highly absorbing material. So that's the absolute absorbing boundary condition, right? So that's the difference between PML. The boundaries don't have a thickness of certain cell size, while in case of absorbing boundary conditions, you specify a region around the cuboid box, the box which encloses the entire simulation design, and that box has got a certain thickness of cells. Okay, so that is absorbing boundary condition. So those things we will see once we do Fdtd simulation. Now this can be done in pathwave EMPro, okay, which is Keysight EMPro, or it can be done using Xfdtd, right? So that both tools are capable of that. Now going to this one, which is called Altair. Now this is a tool in its own league. It's far ahead of all other tools because it implements not only a legacy method of moment, but it implements what is called multi-level fast multipole method of moment. Okay, so this method of moment is a parallelized algorithm for the method of moments, right? So this runs faster compared to the method of moments which you see in case of ADS, or you see in case of Feko. The regular legacy method of moment is implemented, but then you are doing multi-level fast multipole method of moment in case of that. That's one thing. Another thing is here the structures can be very large. For example, it is used for radar cross section, where you can put in an entire car. For example, you can see over here there's a car, and this is a monostatic radar pattern, RCS, radar cross section of that car in in azimuth, right? So now this one you can do a bistatic radars, and you can do multistatic radars, right? You can do a radar cross section for various objects. Now how is it able to do it? Okay, it is going to use some form of a when the object is much smaller, when the space, computation space, is multiple wavelengths. right? Then in that case you apply something called physical optics, or PO, or you use something called geometric optics, or GO, or these are all asymptotic techniques, or you use something called universal theory of diffraction, or UTD. Okay, physical theory of diffraction, which is called PTD. Then there is something called general theory of diffraction, which is GTD, right? So PO, GO, PTD, UTD, GTD, okay, all these are available in Feko. Okay, so if you are going to work with something like inverse SAR problem, right, or something like antenna placement problems, these are going to run much faster in case of Feko compared to any other classical techniques of electromagnetics. Now these are optical techniques. Now so that's the difference between Feko and rest of them. Feko is much ahead in terms of algorithms, right? You have numerous choices here. So Feko is one which can be used. Other one is, now this is called AWR, which is again a method of moment, but then that method of moment has been acquired by Cadence. Now it works with their Cadence Virtuoso, right? So this is similar to what ADS has as a momentum, right? So that's AWR. Then you have something called CST Studio. Now this allows you to do your Fdtd, and this also allows you to do FEM, right? So these solvers are there in case of CST Microwave Studio. Okay, so there's nothing much here to talk about. Now this one, Multiphysics Solver. Now all of these in the past, whether this Keysight or Keysight ADS EMPro, or its Fdtd, or its Feko implementation, or AWR implementation, or CST implementation, all these are Laplacian solvers. It means that when we say curl of H is equal to J plus dou D by dou T, now that J component is not there because there are no charges in the medium. That's what it is assuming. So curl of H becomes dou D by dou T, curl of E becomes minus dou B by dou T. Again, there are no magnetic charges here, right? So these two equations are without the charges, okay, or without the conductivity. Sigma E is also there. J plus sigma E plus dou D by dou T is equal to curl of H. Now here that is not assumed, right? So these are all Laplacian solvers. Okay, so whenever you say you have got a charge which moves under the effect of a field, okay, then these simulation softwares cannot be used. Okay, then in that case you have got COMSOL. So that is why you cannot do active devices in these simulation tools, because they are Laplacian solver. They don't deal with carriers. Okay, they don't deal with carrier distributions. Okay, because they are based on assumption that there are no charges which move under the influence of fields. Okay, so these are all Laplacian solvers, while this one solves the partial differential equations using different methods. Runge-Kutta method may be one of them, right? So it uses different equations, different algorithms to solve partial differential equations, where fields are besides the fields, the charges are also included. So COMSOL is a multiphysics software which can do EM simulation, but then it can also do devices, while in all others you cannot do devices, right? So we'll see some examples of doing devices in COMSOL. Okay, moving further, we have one more which is called Lumerical. Now this has been again bought out by ANSYS. Now ANSYS is a fluid dynamics software company, or it has to do with mechanics. Now recently they have been acquiring Ansoft and other people who do the electromagnetic part plus the optical part. So Lumerical was acquired by ANSYS, and this Lumerical is again you can say it is a FVM based solver for a certain eigenvalue problems, like cavities, resonant cavities and stuff like that. But then it has its own what you call discrete Galerkin methods. Okay, they are method of residues like FEM. FEM is the generalized family is Galerkin methods, but then the specialized form of that is the FEM, right? So it uses a different kind of a algorithm, right? So this is a discrete Galerkin method which is used in Lumerical to solve optical problems. So as we move towards terahertz, we might be seeing more use of technologies which are close to optic, right? So as the frequency goes up. So this is a brief review of different simulation tools, and I am going to just list them out now. Okay, and the reason for listing them out is very simple, that you keep in mind various tools which are available, various EM simulation tools. Okay, so what you have to keep in mind is what they are used for. As a designer, you are more interested in what you can use for what. Okay, so I'm going to start with the ADS momentum. Okay, now this allows you FVM or FEM you can call, and MOM or method of moments, right? And this should be used for, this can be used for planar circuits because the entry tool is planar. Okay, so I would say used for planar circuits. Now for example, ICs or your RF boards or PCBs or laminates, that will be called planar circuits, right? So this is used for that. Now the next one is EMPro. Okay, now this EMPro allows you to do FVM, and it allows you to do Fdtd, finite difference time domain method. Now this is a time domain method, while FEM is a frequency domain method, right? And another thing, FEM, the size of computation is limited, and Fdtd, the size can be very huge. It can be multiple wavelengths. Another thing is that your FEM is not so good for parallelizing. So you cannot run multiple, you can run multiple CPUs, multiple threads, but as such the classical technique is not so good for parallelizing it. Now Fdtd can be made highly parallel. Okay, you can have different regions where you can separately compute the fields and then you can put them together. So this is more prone to what you call parallelism. Okay, so now this is used for you can say this is used for 3D structures, and these 3D structures are small. So I can say small, used for small 3D structures. Now if you try to use EMPro for doing RCS, for example, or antenna placement problem, it is capable, but you will sit for a long time, right? Because it is based on a classical technique, right? Okay, so that's what EMPro is. The next one was Hfss, high frequency structure simulator. Okay, now this is a FVM based. There is no Fdtd in here, and this is used for small 3D structures. Okay, so you should know the choice of tool. Okay, now these are all going to be Laplacian solvers. So I'm going to put so there are no charges. Laplacian solvers. Okay, so because I included COMSOL in the list, that's why I have to put this specifically. Oh, sorry. Okay, so this is a Laplacian solver. Okay, all these are Laplacian solvers, so I'm just going to do copy paste. Control C, comma, Control V. Okay, so that is Hfss. There is a smaller, lower frequency version of this, which is usually used for simulating generators, motors, dynamo, which is called Maxwell. Okay, similar technique, but that's used for low frequency stuff, right? So for electrical machines, so that's called Maxwell. Okay, so now the next one, okay, in the list is Xfdtd, RAMCOM's Xfdtd. Okay, so as the name says, it is going to be a finite difference integral method, right? Fdtd. Okay, and this is used for mid to small to mid-sized 3D structures. Correct? Again, it is a Laplacian solver only. Right. So this is Xfdtd. Next one I am going to pick up in the list. Hang on a second. Okay, so we are done with this. We are done. Okay, Altair Feko. Okay, so Altair, so it's going to be Feko. Okay, now Feko. Okay, so here also it is a Fdtd method. Okay, Feko is asymptotic techniques, PO, GO, PTD, GTD, UTD, right? Then it has got multi-level ML fast multipole method of moment. Okay, so that's it uses. Then it has a classical MoM also, and then it has got a FVM. Okay, so these all are available in case of Feko. Sorry. Okay, and this one is used for RCS inverse SAR and what you call antenna placement, right? So that's that. And again, these are all Laplacian solvers, right? So after Feko, we also have let me just go through. So we have Feko, then we have got AWR, okay, which is classical MoM. So this is a very small tool, AWR. Okay, this is going to be MoM, and this is 2.5D. It is used for planar circuit, which means that you cannot do cube package designs like QFN, DIP, or ball grid array. You cannot simulate 3D structures in here. You cannot do a horn antenna, for example, because this is MoM, right? Sorry. Okay, now the next one I'm going to summarize is CST Studio. This has both FVM and Fdtd. Okay, CST Studio. It has got FVM and Fdtd. Okay, and it is used for small 3D structures. Okay, the next one, and we are going to, in this series we are going to see all of these closely. Next one is called COMSOL, right? And COMSOL can do classical FVM. Then it has got PDE solvers, and this one can be used. So this is also Laplacian. So all these are Laplacian solver. Let me just add them. Okay, so that's a Laplacian solver, and this one is also a Laplacian solver, which means no charges. While this one used for it can be used for, there's no limitation on 3D structure side. So I will say used for 3D passives as well as actives, and this is not a Laplacian solver. Okay, so that's COMSOL. Okay, now ISE TCAD is in the same league as COMSOL, or Centaurus TCAD, which can do passives as well as active. Well, I'm not going into detail of that. Then there are some others, okay, which are used for, you know, very small nano devices like FinFETs, right? So I'm not going to go into multiphysics here. Okay, so now the next one is called Lumerical, and this is Lumerical is a FVM, and then it is a discrete Galerkin methods, different methods, DI discrete Galerkin method. Okay, and it is used for 3D structures which are small. Okay, used for small 3D structures, and these are again Laplacian solvers. Sorry. Okay, so what do we have? We have different tools, and these different tools can be chosen for different applications, correct? And now you're very sure which one to use where. Okay, so let's see how much time we have taken. We have taken 38 minutes. Okay, so I'm gonna stop here. I'm going to put in the next session, I'm going to start with AWR momentum, right? And how to do things in momentum, right? So then this is for the next one. So thanks a lot. Thank you very much. So I'm going to stop here.